Okay, so today we're going to look at a couple topics. We're going to start with this heat of solution. Now, normally when we're in class, what we would do a little lab activity to go on along with this. So unfortunately, we can't do that, but I'm just going to include a couple links to videos in the Edmodo post today, and that will link to the two little, there, it was just sort of a mini lab, but it will link to the two experiments that we would have done to show this process. So when we're talking about heat of solution, okay, so we're talking about when solutions form, what happens to, sometimes temperature changes can occur. Okay, so oops, let's just figure out my pen here. All right, so, oh, that's not right. Okay, there we go. So energy changes are involved when solutions form. So if a liquid or solid is being dissolved, energy is required to break those attractive forces. So if you think about the last lesson we did and we looked at ionic substances dissolving versus molecular, you think about those ionic bonds between a positive ion and a negative ion, there's a strong attraction there between positive and negative. So in order to split those ions and separate them out in the process of dissolving, we need energy to break apart those ionic bonds. So dissolving a liquid or solid, we need energy to break the attractive forces between ions or molecules. So in the molecular compound, you're simply breaking one molecule away from its neighboring molecule. And there's still going to be an attraction there, intermolecular forces. So those attractions need energy to break apart. So when energy is required, we call this an endothermic process. Okay. The attraction between the solute and solvent particles during dissolving releases energy. And when energy is released, we call this an exothermic process. Okay, so in one, energy is required, in the other one, energy is released. The difference in the heat absorbed to break bonds and the energy released by the attraction of solute to solvent particles is called the heat of solution. Okay, so if the amount of energy absorbed is greater than the amount released, the process is endothermic. And what will end up happening, what you would feel in an endothermic reaction, or what you could record with a thermometer, is you will feel that it's cold or cool. Whereas in an exothermic, so if the amount of energy released is greater, the process is exothermic. Okay, so it's releasing heat. So it's giving off heat. So that means the container will feel warm or even hot. Okay, this one is using up that energy, right? So when it uses up that energy, the resulting temperature has decreased. So let's just draw a little diagram to show the difference. If this is energy here in an endothermic, okay, so this would be the amount of energy absorbed, and this is the amount of energy released. Okay, so you can see the amount of energy absorbed is greater than the amount of energy released. So this difference here is heat absorbed. Okay, so when it's absorbed, it's used up. That means you're going to get an overall temperature decrease. Okay. Over here, here's the energy absorbed for exothermic, and here's the energy released. Okay, so your difference here is this, and this would be the heat released. Okay, so this is going to feel warm. Okay, so it would be at this point that we would stop and we would actually do one endothermic and one exothermic reaction. So I've just found videos that show these two reactions, so you could pause here and check those videos out. Obviously not as great as doing it yourself, because when you do it yourself, you actually feel the temperature change. In the videos, you just see the temperature change on a thermometer, but it will have to do. So we've got ammonium nitrate would be our first one, and it's dissolving in water. And you'll see, or if you've watched the videos, you'll see that it's an endothermic process. So the container feels cold, or in the video, you see the temperature steadily decrease as more and more of the ammonium nitrate dissolves. So the applications here, ammonium nitrate is used in cold packs or ice packs, you know, the ones where you squeeze the interior bag and it breaks, and then you shake it around and it ends up turning into an ice pack. So when you squeeze that bag, you break a bag of water, which mixes with the ammonium nitrate. And as you mix them together and shake them, the solid dissolves, energy is absorbed, and it makes the bag feel cold. Okay, the other one that we would do to show the exothermic process is calcium chloride dissolving in water. So calcium chloride dissolves in water, it releases heat. So when it releases heat, it's exothermic and it feels hot or warm. So an application of this is calcium chloride is used to melt ice on roads because it releases a lot of heat when it dissolves. It is also found in some heat packs. So kind of the similar idea to the ice or cold packs. Some heat packs contain calcium chloride, so when you mix or crack it or shake it, it ends up producing heat for a period of time. Okay, so we're going to kind of jump to the next, because that would have been a little mini lesson followed up by a lab. We're going to jump over to the next set of notes, and we're going to not do the whole set, but part of the set today, and then we'll finish them up on Monday. So this next topic has to do with solubility, and what dissolves in what, and what are some things that affect solubility. Okay, so rules for solubility. In general, like substances dissolve like substances. So the rule is like dissolves like. Okay, so what that actually means is if a substance is polar, it will dissolve a polar solute. So a polar solvent dissolves a polar solute. The other thing a polar solvent will dissolve is an ionic compound. The reason you can consider an ionic compound like a polar substance is because of we know polar substances have a charge separation, and ionic compounds also have charged particles, right, ions that they're made up of. So because of those charges and the charges in a polar substance, that allows them to dissolve in one another. Unlike materials are not soluble. So you couldn't dissolve a non-polar substance in a polar one. So non-polar solvent will dissolve a non-polar solute. Okay, so they have to be the same. Non-polar dissolves in non-polar. So an example, liquid kerosene, which is non-polar, will dissolve solid iodine, which is also non-polar. However, iodine is not going to dissolve in water, which is polar. It might dissolve a tiny bit, but not much. So we can use this general rule to predict whether a particular solute will dissolve in a given solvent. So the rule, we just always remember, like dissolves like. Okay, so here are our solutes. This is what's getting dissolved. So if we have a polar solute and a polar solvent, those are like, so we would say dissolves. If we have a polar solute and a non-polar solvent, those are not alike. So I'm going to say, instead of doesn't dissolve, I'm going to say insoluble. Insoluble means it won't dissolve. So here, another way you could say this is soluble. Okay, now we have a non-polar solute, and you're trying to dissolve it in a polar solvent. Well, they're not alike, so that's insoluble. And if you have a non-polar solute and a non-polar solvent, they are alike, so they are soluble, or they would dissolve. Now, ionic, okay, ionic isn't the same as polar, but because it's made up of charged ions and polar substances have a charge separation, they're alike enough. So ionic solutes are usually, we'll say, soluble in polar solvents, but ionic in non-polar would be insoluble. Okay, so ionic substances will dissolve in a polar solvent, but are not soluble in non-polar, because so we just kind of filled that in the chart. Ionic substances are made of charged ions, so they react in a similar way to polar solutes. So just to kind of connect to some topics you might have learned or maybe are learning in biology, fats are non-polar. Okay, so the human body requires several non-polar vitamins, such as vitamin A, vitamin D, and vitamin E. We require fatty foods to absorb these vitamins. So I don't mean like French fries and unhealthy fats, but there's lots of healthy fats that you can have in your diet, and we need those healthy fats in order to absorb these important vitamins, because we need something non-polar to absorb the non-polar vitamins. Okay, so these vitamins we need these fatty foods to absorb them because they cannot dissolve in water. They're not water soluble. They are known as fat soluble vitamins. So just to get a sense of what are some polar and non-polar substances, here's a list. So we know already that water's polar. Alcohols are polar. So here's a bunch of different types of alcohols: methyl alcohol, ethyl, isopropyl. These are like organic compounds. Acetone, acetic acid, which is vinegar. So lots of different types of acids are polar. Non-polar substances are things like hydrocarbons. Okay, so octane, for instance, is a hydrocarbon that can be found in gasoline. We will learn more about these in the organic unit. Greases, so anything that's sort of greasy or waxy So greases, vegetable oils, mineral oil, tars, waxes, all of those are non-polar. So that's one you can definitely imagine. Vegetable oil, for instance, we know does not mix with water. Those two things are insoluble. Okay, one's non-polar, the other one's polar. Okay, so how do we know how much of something, like a solid, will dissolve in a liquid? So the solubility is the amount of solute that will dissolve in a specific solvent under given conditions. So the solubility of a particular solid solute in a liquid solvent depends on a number of factors. So we're today just going to look at those 3 factors. And then on Monday, we'll get more into how to use solubility curves. So that starts to get more into the calculations and math type stuff that we can do with this unit. Okay, so one of the factors that would affect how much you can dissolve is the nature of the solute and solvent. So this just sort of reiterates what we already talked about. Polar solutes dissolve in polar solvents. Non-polar solutes dissolve in non-polar solvents. And a non-polar solute dissolves in a non-polar solvent because the only attractive forces between molecules are dispersion forces. And these forces are similar for both solvent and solute. So our general rule, like dissolves like. Okay, so this we just finished talking about. So one of the factors that affects solubility is, whether the two things are compatible. Are they alike? The second factor is temperature. So this you can likely relate to if you even think of dissolving sugar in a hot cup of coffee or tea versus dissolving sugar in, say, like just cold water. You'll find that that spoonful of sugar will dissolve a lot more quickly in the hot liquid. So temperature plays a role in how soluble something is. If you want to dissolve more of something, typically for most substances, you can do that by increasing the temperature. There are exceptions to that, but most solids become more soluble as the temperature increases. So the solubility of most solids increases with increasing temperature. So I'm just going to scroll down here. This is a solubility curve. Now, I included, there's 2 kind of appendices for this part of the unit. One was the electronegativities table that we referred to in the last lesson. The next one is the solubility curves. So I'll just switch over to the one that you have. You have this, it's not the best, it's a little bit blurry, but this is the one you have. This is the solubility curves chart, and it's just sort of condensed here to look at. Okay, so what this shows is solubility. So on the y-axis, you've got how many grams of solute can dissolve in 100 grams of water. Okay, so this would be 10 grams can dissolve, 20, 30, and so forth. And this is the temperature. And the temperature increases going this way. So you can see most of these substances, they curve up and to the right. Okay, some have very steep curves, some more gradual, like salt here, sodium chloride. Its solubility increases as temperature increases, but it's not that drastic, right? It's a very small slope. Okay, so if we were to look at one, say sodium nitrate, here's sodium nitrate. So at 0 degrees Celsius, you can dissolve about 75 grams of sodium nitrate in 100 grams of water. But if you increase the temperature to say 40 degrees Celsius, now you can dissolve 105 grams of sodium nitrate in 100 grams of water. So this is just giving for each particular substance, how does the solubility change? The solvent has to be water, and this is all based on 100 grams of water. So how does the solubility change as we increase the temperature? You'll notice there are two that decrease as the temperature increases, and we'll talk about those in a second. But the majority of the lines on this graph go up and to the right, meaning that they get more, you can dissolve more and more and more of them as the temperature goes up. Okay, so the graph below shows solubility of some solids versus temperature. In some solids, however, the solubility decreases as the temperature increases. So the two on here are the NH3 and the cesium sulfate, I guess that would be. Okay, so if the temperature drops, if it's an endothermic reaction when the solid is added, the solubility decreases with increasing temperature. Okay, so that would be these two here. So that means that when they are dissolved, they actually absorb heat, the temperature decreases, and they get less and less soluble over as the temperature increases. Whoops, sorry, I screwed that up. Let's go back here, hang on. Okay, sorry, let's reverse. If the temperature drops throughout the process of dissolving, if it's endothermic when the solid is added, the solubility usually increases with increasing temperature. Okay, so those would be the vast majority of the ones on here would be endothermic. Two examples are the potassium nitrate and sodium nitrate. If the temperature rises, sorry, I got these two backwards, but now I've got it right. Okay, so if the temperature rises when the solid is added, so if it's exothermic, it's releasing heat, then the solubility decreases with increasing temperature. So the two on here are NH3 and the cesium sulfate. Okay, now this is the less common scenario. It happens, but more often than not, it's endothermic and the solubility increases as the temperature increases. Okay, the last thing that we're going to look at is the third factor that affects solubility is pressure. Now, pressure is not going to have a very large effect on how soluble solids are. It's very small. And the reason being is because pressure doesn't affect solids very much. The particles are already so closely packed together that changing pressure really doesn't change much about a solid. This factor comes into play when we start looking at gases, how they dissolve in a liquid. Then pressure becomes very important because gases, pressure has a great influence on a gas. So as we'll see later, pressure has a large effect on the solubility of gases in liquids. Okay, so at this point when we're talking about solids, pressure really doesn't change much. It's the temperature and the nature of the solute and solvent that are the most important with solids dissolving in liquids. So the very last thing that we're going to look at today is just some generalized things about solubility curves and what saturation means. And then on Monday, we'll get into detailed problems where we solve using the solubility curves. Okay, so let's just define a few things here. An unsaturated solution, and you probably have already a sense of what these terms mean. You've probably heard them before, but an unsaturated solution is a solution that holds less than the maximum amount of solute possible at a given temperature. So that means that you could still continue to add more solute and it would continue to dissolve, right? It hasn't reached its like maximum capacity for the amount of solute that can dissolve. Whereas a saturated solution is a solution that holds the maximum amount of solute possible at a given temperature. So that means, let's say you're dissolving salt in water. If you've added salt and stirred it up and dissolved it, if you've reached the point of saturation, if you then went to add more salt to the water, it wouldn't dissolve. You could stir and stir and stir, and it just would stay at the bottom of the beaker. When you stopped stirring, it wouldn't dissolve in the water. So saturated is at max capacity for the solute. Okay, undersaturated, it could still dissolve more. Supersaturated is maybe one that you haven't heard of, is a solution that holds more than the maximum amount of solute possible at a given temperature. So you might think, well, how is that possible, seeing as I just said, if you added more to a saturated solution, it wouldn't dissolve. So the way you can make a supersaturated solution is you can heat up the substance. So you can heat it up so that you can dissolve more of the solute. And when you do that, you can create a supersaturated solution. So it can be made by saturating a solution at high temperature. And then if you allow it to cool very slowly, the extra solid will stay dissolved. So that's how you would create a supersaturated solution. So the solution will actually hold more solute or solid than it should at the lower temperature. Okay, so those are kind of tricky to come up with, but that's how you would create supersaturated. Heat it up so that you can dissolve more, and then very, very slowly cool it, and it will actually keep that extra solid dissolved. So on a solubility curve, like we looked at before, they graph the amount in grams of solute that can be dissolved in 100 grams of water at different temperatures. Okay, so the only thing that we're going to really focus on in terms of reading these solubility curves today is how to determine if something's saturated, supersaturated, or unsaturated. So this just kind of shows if you are given a particular number of grams and temperature. So if you wanted to know, for instance, let's actually go back to the curve so I can show you a specific example. If I said determine whether the solution of sodium nitrate is saturated, supersaturated, or unsaturated, and then I gave you an amount of grams and a temperature, you could find that point on the graph and you could see where it falls in relationship to the curve. So let's say I said if there's 110 grams of sodium nitrate dissolved in 100 grams of water at 20 degrees Celsius. Okay, so the point would be right here. Okay, is that solution saturated, unsaturated, or supersaturated? Well, it's falling here. The saturation point would be about 88 grams per 100 grams. We're at 110. So that's way more than what the saturated solution can hold. So that means that the solution is supersaturated. If I said you have 88 grams of sodium nitrate dissolved in 100 grams of water at 20 degrees Celsius, well, that's right on the line. So that would be considered saturated. And if I said you have 65 grams of sodium nitrate dissolved in 100 grams of water at 20 degrees Celsius, well, that's down here. Saturation is 88 grams, you have 65. So there's still more, you can still continue to add more. So if the point fell here, that would be considered unsaturated. So that's just what this is showing. On the curve is saturated, below the curve is unsaturated, and above is supersaturated. So that's one thing that you can determine from reading these solubility curves. The only other thing we're going to talk about is if the curve sweeps up to the right, the solid increases in solubility with increasing temperature. And if it curves down to the right, the solid decreases in solubility with increasing temperature. So the notes, we're going to stop there with the notes today. The worksheet that follows, there's a lot of questions to answer, but I only want you to answer questions 1 through 5. The rest of the questions we'll learn how to do on Monday when we go into specific problems with solubility curves.